Welcome. Yes, of course, you can also use the icon with the thumbs up in the panel at the bottom of your at the bottom of your screen. Okay, so welcome everybody. Welcome back to those who were with us also yesterday at the plenary. Welcome to this high-level expert workshop on climate and adaptation modeling, and in particular in this session, which is devoted to integrated assessment modeling. Let me introduce very briefly myself. I'm Francesco Bosello, and I'm coordinator of the tender on adaptation modeling with the DG Climate. That is also the inspiration for this workshop. I'm also professor of economics at the University of Milan. A little bit of background. This workshop is exactly part, as I mentioned, of this tender that has been is being developed with the DG Climate, and the main purpose of this work is to stock take and propose some improvement on the available knowledge related to adaptation modeling and their application. I would ask everyone who's not speaking to mute the microphone, or Silvia, you should mute your microphone because we hear some background noise. Thank you. Okay. And the main purpose of these, the purposes of these work and workshops are two. One is to understand what is missing, so the gaps that adaptation modeling face in providing useful support to the policy action. And the second one is also to understand how this information could be more conveniently and usefully conveyed to the final users. So this, having this in mind, the research team that developed this work is composed by, let me just quote the all the people that contributed to this research effort. So institution, not the people, otherwise it would be too long. So CMCC is the coordinator of the tender, so the European Euro-Mediterranean Center on Climate Change. Then we have the Institute for Environmental Studies of Amsterdam, Deltares, and Paul Watkins Associated. Let me also recall that after this session, there will be other parallel session going on all the day, and in particular, if you are interested, we have at 12:30 a plenary session, a short plenary session, 30 minutes, where all the rapporteurs that are assigned to each of the parallel session will present a very quick summary of what has been discussed. So if you're not able to follow all the parallel session, you may want to attend the plenary at 12:30 to have a short recap. And all this said, I should stop and leave immediately the floor to our first speaker, which is Raghav Pant from the University of Oxford, with his presentation, Advances in Climate Adaptation Modeling of Infrastructure Networks. Let me very briefly remind the rule of the game. We have a tight, we have basically 60 minutes for the session, so the presentation should last between 10 to 12 minutes to leave 3 minutes to one burning question from the audience. You are very welcome to write your question on the chat, and I will convey it to the speaker. So, Raghav, you can start. Thank you for joining us, and we are looking forward to hear your presentation. Silvia, you should unmute Raghav, I think. Okay, perfect.
Hi, I assume everybody can see my screen by now. And yeah, thank you very much, Francesco, for introducing me, and thanks a lot for giving me this opportunity to present at your conference. So yeah, as Francesco said, my topic is on looking at infrastructure networks and looking at climate adaptation modeling work we have done on infrastructure networks. And my focus is more on the impact side of things than the climate hazard side of things. And the kind of infrastructures that I'm looking at are these lifeline networks like energy, transport, water, waste, telecoms, and flood management. And we understand that these infrastructures are very important for climate adaptation, for disaster risk reduction, for meeting the sustainability development goals. So, and they play a very vital role in socioeconomic prosperity. And one of the things that is happening that we kind of see happening a lot is that large infrastructure investments are being made at a rapid pace, but then newly built infrastructure or existing infrastructure that is old is being constantly eroded by climate disasters. And when we go and talk to stakeholders, they always say that in order to understand better investments, they need to understand the wider aspect of infrastructures. And there's a lack of system assistance tools and models that can kind of explain the role of infrastructures in wider socioeconomic terms. And the kind of questions that we are facing in our work when we work with stakeholders, and I'll cover some of the studies in the next slides of my talk, but the kind of questions that we are facing from them are like, how do we quantify vulnerabilities and risks to these network systems? And another very important aspect is this whole idea of understanding indirect impacts of infrastructure failures. Most of the times when infrastructure investments and infrastructure are understood in the context of building climate resilience, most of the quantification is done in terms of direct physical asset damage losses. People just quantify what is the value of your building or your road or your electricity substation, and then build their investments based on, or the risk assessments based on just the value of the asset that is damaged or disrupted. Very few times people try to understand the wider economic impacts that an infrastructure failure might have. And then people want to understand what kind of climate resilience investments and interventions should be done to reduce vulnerability of critical segments of a network that can overall enhance network resilience. Because the key over here is not just to protect an individual asset, but to also have a more robust and functioning network as a whole. And then in order to kind of understand the systemic perspective, because an investor or a national planner will not have a lot of money to invest in every vulnerability and risk on their network. So the idea is also that they should be able to identify systemic impacts so that they can prioritize investments. And these kind of questions we get are, I think they are simple questions to ask, but the answers are very difficult because infrastructures are complex systems. And one of the things that we have tried to do in our group is adopt a system of systems perspective. And we have a lot of papers that we've written on this system of systems modeling perspective, infrastructure networks. And if you're interested, I can share them with you after this talk. And the idea is that infrastructure exists as these interconnected networks. And these networks are communicating, talking to each other, connected with each other, connected with society, connected with the economy. So failures propagate or cascade from one infrastructure network. So understanding one network by itself is half of the story or an incomplete story. You need to understand the whole systemic perspective. And in this talk, I'll specifically concentrate on transport network analysis that we have done, because we have done some adaptation quantification on that as well. In the paper that I submitted to the conference workshop talks about other studies in which we have looked at interdependent failures of, from electricity to telecoms and other networks for a study we recently finished for the UK's National Infrastructure Commission. But in this talk, I'm going to give you a bit of a flavor of a framework in action of transport adaptation modeling. This is some work we did with the World Bank in a bunch of projects in Argentina and Vietnam. So what we've done is we've built this framework, if you can see on the slide. So you have the hazard information at the top. You integrate it with a network, geospatial infrastructure network, and you identify, do an exposure analysis, and try to understand what are the direct asset risks. But then you kind of look at these indirect effects in terms of the mobility of transportation. Specifically in our studies, we looked at freight transportation mobility along the transport network in terms of where freight is supposed to go, and if it is disrupted, then what are the rerouting options along the network. And if there are no rerouting options, then what you see is that there are disruptions in the freight. And that also results in, if you look at the very bottom layer of this figure, if there are disruptions in freight, because freight is carrying things of economic value, so that disrupts economic supply chains in a country. And we kind of integrate that with this kind of high-level macroeconomic input-output models to kind of say that if a certain amount of commodities of freight are disrupted in a country's transport networks, that creates a cascading effect on the economic supply chain. And this helps us quantify these indirect economic impacts. And if you're an investor, you'd use this information of understanding indirect impacts with the direct impacts. And then you think about the level of investment you need to make. And the benefit of that investment is that you're going to avoid that level of risks in terms of direct and indirect impacts. And this is how you kind of decide how to make your investment decisions. This framework is kind of, in a very simplified ways, has helped convey information to stakeholders on kind of understanding how to think through the problem of networks and climate risks and adaptation investments. So very quickly, some of the work that, for example, we've done in Vietnam and Argentina is first to map out the system. So what you see in these maps are the road networks of these countries. And on these road networks, we have captured all the important freight that is going through important linkages or important routes along the road networks of these countries, and we have kind of associated the economic value associated with them. So this kind of maps in themselves are kind of interesting information to just show the economic linkages in a country. This requires a lot of data information, and we've worked with governments and with the World Bank in these countries to build this kind of information. And what you associate with this is then the risk information, that if you intersect all these different networks with different hazards, for example, in Vietnam, we looked at landslide, flooding, storm failure. So we got probabilistic risk, hazard maps for flooding, for landslides in these countries through government agencies or through other organizations. So the idea over here is you look at exposure and then the resulting economic impacts by intersecting flood hazards with probabilistic flood hazards with the networks, and looking at the failures of individual roads, and then looking at the economic value associated with it that is disrupted. And this kind of map in itself has been very useful in kind of giving information to the stakeholders and telling them, look, these are the risky roads or roads most at risk in your country, and these are the assets you want to protect. And one of the, as I
sorry, just I hate to be so strict, but you have 3 minutes more or less left.
Sure. Thank you very much. So one of the, as I said, the messages that I want to convey through this talk is this whole idea of indirect economic impacts, which are very important in understanding systemic risks. So if you look at the graph over here in the studies that we have done, for example, in Argentina, one of the things you see in this graph, you see the color in pink, which is the direct economic impacts, which is basically by direct intersection and looking at the asset value. And these direct impacts are substantial, but so are indirect impacts. If you start thinking about indirect impacts are influenced by how long disruptions last. So if a disruption lasts 10 days or 20 days or 30 days, you see like your economic indirect impacts keep on increasing. And sooner or later, they become the predominant impact. So this kind of shows a very interesting thing about also planning your resilience activities in order to try to lower the duration of disruptions, because indirect impacts will grow substantially if the longer the disruptions last. And this kind of information has been very informative for stakeholders to understand that large-scale systemic impacts over long durations will have greater impacts on transport networks or infrastructure networks. And then quickly looking at some sort of investments or climate adaptation options within, for example, Argentina and the study we do. For example, these are related to simply enhancing roads, upgrading them to better standards, and there's a cost associated with them. So you have a cost, and then you have a benefit, and you can do an adaptation assessment. And this kind of gives information to stakeholders to then identify critical sections. If you look at the very right-hand side map, the third map, the benefits cost ratio map, this basically tells you which roads you can invest. You should prioritize for investment in a country based on benefit cost ratios being the highest. All the roads shown in red have some of the highest benefit cost ratios in terms of avoiding economic or large scale risks. And we have built a tool within Argentina to convey this information to stakeholders. And this was being used by the Department of Transport in Argentina. And this is kind of very useful that they can now interrogate their roads and in the country and integrate them with climate risk information and understand benefits and costs of adaptation. And same, I mean, they can prioritize where the important roads are. I think this is my last slide. So what is the value of all of this work? The value of all of this work is that it helps create this comprehensive set of models and tools to understand systemic impacts. And this the emphasis is on systemic impacts. And it helps create scientific evidence to understand for governments so that they can then look at the level of investments they need. And this is definitely a first order kind of screening and prioritizing effect. I would always say that you need to do detailed site investments following from this. And in Vietnam, for example, one of the interesting things that was done was this helped them understand the levels of nationally determined contributions that they need to make to meet Paris Agreement, the nationally determined contributions, climate adaptation. So this was kind of very useful exercise for us. So yeah, with that, I kind of come to an end to my talk, and thank you very much for your time and attention. Thanks a lot.
Thank you, Raghav. Just if you can answer in 1 minute the question. So very nice talk, very interesting. I took the advantage of being the moderator to raise the question, and which is all these approaches, which is something like which is relevant for also our research here in during this tender. All these approaches, how easily could be transferred or used by policymaker? Is this something or a system of tools that could be also used directly by them, or they need a particular technical support? So what is the interface with the policy action? So just 1 minute, 30 seconds to answer this quite
well, I definitely think it's not an easy kind of, I mean, if you're talking systemic impacts and whole kind of modeling of a country's network, it's not a simple exercise. So we have tried to work with governments and have work with technical experts within governments, and stress that this requires like initial exercise right from the beginning to get them involved, understand every step, so that they can kind of incorporate them into the practices. And that kind of, we find that if we train and convey our research to them during the process of creating these tools, that is more effective than just creating a tool and just giving it to them and saying like, okay, now just use it, because then they haven't really understood the whole process behind it.
Okay. Thank you very much. So we move immediately, very interesting presentation. We move immediately to the next presenter, which is Thorsten Wagener from the University of Bristol. The presentation is on the evaluation of climate change impact models for adaptation decisions. So perhaps a more critical view on what these kind of tools are able to do and what they are not. So Thorsten, thank you for joining us, and the floor is yours.
Let me just share my screen with you. So, good morning, everybody. Thank you for the invitation to this very interesting and diverse workshop. So I'm a hydrologist by training, but today I would like to talk a little bit about another interest of mine, which is how we evaluate and justify and test the robustness of models. In this particular case, climate change impact models for adaptation decisions. in a changing world, when we look at climate change or other changes in the environment, what we're interested in is having mechanistic models so that we can look at how the system will change if the boundary conditions change, the drivers change. So we need causal relationships between variables in our models, rather than empirical models that just reproduce correlations of the past. Once we have these models, say whether these are infrastructure models like Raghav just showed, or flood impact models or something else, then the additional aspect that we need to have is that we somehow need to justify or validate these models. We need to somehow demonstrate that the models are capable of doing what we want them to do. In the past, when we looked at reproducing historical observations, then this justification came largely from just being able to reproduce the data, being able to reproduce historical observations. Going forward, when we look at changing boundary conditions and the focus is on modeling or simulating conditions we have not observed in the past because they're more extreme maybe, then model predictions derive their credibility from some type of diagnostic evaluation of how consistent the model is with the underlying system, and of testing how the model behaves outside the observed range, the observed past. So, but if we look at what people are actually doing, this was a nice recent study by Ecker et al., where they surveyed a large number of researchers and policy analysts in academia, policy organizations, and industry, how they were essentially validating their models. Then it was predominantly by showing that their model could reproduce past behavior, could fit the data. However, they also asked them further questions, and this is one of them where they gave the participants a statement saying model output is more important than the model structure for the validity of models used for scenario exploration specifically. So how much is really the model output the main focus for validating our model? And the vast majority, roughly 80%, said, no, we don't think so. We think that the assumptions we made in our model, the relationships, the uncertainties that we have in our models play an equal role, at least, in justifying the model and its use for scenario exploration. So this result is similar to some of the results we had when doing scenario analysis workshops, where stakeholders very often were mainly interested in understanding how the model was conceptualizing reality and whether that conceptualization was consistent with their understanding of how the real system worked, rather than just seeing that the model could reproduce some data. Now, what we do is we develop tools and apply tools to do an assessment, an evaluation of assumptions, of choices, of uncertainties, and how much they influence the model output. So what we're trying to do is, rather than just looking at the model output, we're trying to look back inside the model, open up the hood to understand how the model reproduces the system. So if we take any simulation model or computer model here, then we have on the left a wide range of input factors, so forcing inputs, maybe climate change scenarios, different parameters, so there might be the land use or the network properties. We might have choices like spatial resolution or the equations that we use, meaning the complexity. Do we have a very abstract model or a very detailed high resolution model? If we consider all the options and uncertainties in these inputs, we run these through our computer model, then we get outputs that might be maps like here at the top, or time series, or simply probability distributions or frequency distributions of output, say of flood risk, for example. What we add is we essentially quantify how much the variability or either through uncertainty or choices in these input factor controls the variability in the output. And we do this in a way that you could say, for example, the uncertainty in our climate change projections controls 50% of the variance of our outputs, whereas, for example, land use choice only controls 10%. That means we can understand what dominates the uncertainty in the output. It's important to say that these could be uncertainties in the input, or there could be choices. Maybe it's simply the choice of our resolution of our model that really controls the variability in the output. And we want to look at that in relation to each other. So two very quick, simple examples just to illustrate what this might do. So here's an example of the DICE model, a global integrated socioeconomic climate integrated assessment model. And we might ask, are the modeled intervention levers effective? So are these elements, the parameters in these systems that represent aspects that we might actually change, dominating the output sufficiently so that we can understand what role, for example, land use change might have in climate adaptation. So in this case, the italic values here are the parameters. So the model reproduces the resources, the labor market, the socioeconomic system. It also links the climate in a simple way to the carbon cycle. If we take all the parameters of this model, they are shown here around a circle. And while this looks a little bit complicated, but essentially the only thing I want to point out is that a few of the parameters, 4 mainly, have a bigger gray circle in front of them. And those are the parameters whose uncertainty is dominating the uncertainty in the output of the model. And what we can see in this particular case, this is just one example of course, a range of results. The biggest gray circle is in this case in one of the parameters of the climate box model, which is the climate sensitivity. So how much is the temperature in the atmosphere changing with changing CO2 levels? And we can see that the uncertainty in that parameter dominates, in this case, the output. So if we wanted to, for example, understand how much land use change impacts this model response, then it wouldn't be feasible unless we better constrain this parameter, because the uncertainty is simply dominating the system response. A different example is we might want to understand how dominant uncertainties or assumptions are changing along the projection timeline. And this is another study not by us, by colleagues who showed in a coastal defense vulnerability scenario study very nicely how different uncertainties dominate at different times along the projection timeline. So what we see here is that the parameters or the uncertainties dominating the impact on coastal defense being exceeded is initially dominated by this wave setup parameter. So by a hydraulic parameter, if you like, that explains wave breaking. And that continues till the middle of the century, and then global sea level rise uncertainty, in this case, takes over and controls the output of the model. So the point here is that these kind of uncertainties are not constant in time. So we cannot assess them now with our current situation, but we have to assess them along changing boundary conditions to see what aspects of the model might control our outputs and whether that is consistent with our understanding of the underlying system. So in summary, sensitivity analysis is a suitable way to understand how a model controls its output and whether a model can be effective for adaptation modeling. It's complementary to, of course, assessing whether the model in principle can reproduce the behavior of the system. So I'm not saying that shouldn't be done. I'm saying it's not sufficient. The answers, the kind of questions we can address with our methods are which models, which parameters or levers control the model output, which uncertainties dominate, how does model behavior change with changing boundary conditions, how much influence do model assumptions have on the model output, our model choices, what are the most important elements in our model systems, and therefore where should we prioritize our focus. The tools we developed are available as open access tools in a software package available in Python, R, and MATLAB from the website safetoolbox.info on the right. So they're freely available, and we share them happily with anybody who is interested and like to use them. Thank you very much.
Thank you very much for the very interesting presentation, and also for the suggestions that the importance of always running a global full sensitivity analysis, which is a best practice that is always invoked in any modeling exercises and very rarely put in place, I should say. But just one question also for you to answer in 30 seconds. So because you are presenting, or you are been dealing with the models, both with models quantifying, let's say, the impacts, but also, for instance, a specific case of a model or information specifically designed for an adaptation purpose, like a coastal protection. So do you see if there is some kind of differences between the uncertainty sources in the two areas? So is there much uncertainty, or much relevant, the higher relevance of uncertainty in adaptation modeling rather than in impact assessment? So what's your opinion?
I think the main focus in adaptation modeling is that we're trying to use the models to understand what we can change to maybe reduce the problem, and therefore these kind of studies have to show that the model is capable of doing this, at least in principle, with reasonable assumptions about the uncertainties present, and we find that that's rarely done and rarely shown, and therefore we justify the model because it can reproduce the behavior, but that's not the task in adaptation modeling. The task in adaptation modeling we want the model to do is to show that we can change things, and that this change is realistic under potential future boundary conditions. And I think that it's therefore the methodology to demonstrate that is often not applied or underdeveloped, I would say.
Okay, thank you very much. There is also a nice comment from Almut that I share, but we cannot comment on the comment because we need to move immediately to the next presenter, which is Jana Sillmann from the Center for International Climate Research. Her presentation is on cross-sectoral challenges for adaptation modeling. So perhaps it's something that could help us to deepen the discussion that we just started with the Thorsten presentation. Jana, if you are with us, the floor is yours.
Hello?
Yes, we can see the screen.
Okay, perfect. Okay, so yes. Hello, everyone, and thanks for the invitation. So I will talk about the cross-sectoral challenges for adaptation modeling, and the talk is put together by my colleagues Aspen, Arneth, Anton, all of course myself. We are taking, I'm just trying to get the slides moving. Yeah. We are taking a macroeconomic lens on adaptation modeling, and the previous speaker has already mentioned one possible model in the DICE. Because we are thinking that, or our approach is that we need, for estimation of climate and adaptation and mitigation costs and benefits, we need to incorporate adaptation modeling and adaptation assumptions in the impact assessments globally and nationally. So, and the macroeconomic modeling perspective provides a better insight in the adaptation planning and costs on the national level or even larger regional level. So the other advantage of macroeconomic modeling is that we can take a cross-regional perspective and compare costs of adaptation or interactions between different adaptation measures among different regions, and we can take into account remote impacts and different sectors. So we are using in our work the GRACE model, which is a multi-region, multi-sector dynamic CGE, computable general equilibrium model. It is based on national account data, so it is aggregated on an annual level and on a country level, or even larger regions like Europe, North America. The economic activities in GRACE are represented by different production sectors such as agriculture, manufacturing, energy, services that can interact with each other, as you see on the left side in this figure, and also the exchange of goods and services to domestic and export markets. So there's an interaction between sectors, between producers and consumers, and between regions. And that is all captured in this model, and that's why we can capture cross-sectoral and cross-regional dependencies. In terms of adaptation, there are three main types that can be represented in the GRACE model, which is adaptation in production, for instance, substituting between labor and capital, or the mobility of labor and capital among sectors and regions. And then adaptation in consumption would be, for instance, substituting between imported and domestically produced goods and services, or substituting between different types of commodities. And then there's a third type, is the autonomous adaptation, which is implemented or can be implemented in GRACE. And I'm giving you one example from a recent study to illustrate how we incorporated and looked at adaptation in the context of climate change. An example of economic costs of heat-induced reductions worker productivity due to global warming. So here, this is merging different types of fields. We're using climate data from the EasyMap database, from climate models, changes in climate variables like temperature, humidity. Then we're using, as a heat stress estimation for heat stress, we're using the wet bulb globe temperature based on empirical functions. And then also we can estimate the worker productivity via the hot taps metric. And then we can estimate the economic costs with using GRACE. So the hot taps metric is basically an exposure response functions that was estimated from field studies, giving the relationship between productivity losses and wet bulb globe temperature for different levels of work intensity. So low, for instance, office work, and high work intensity is when you work outside in construction or agriculture. So you have different those response functions depending on the work intensity. And what we get in terms of physical impacts, then looking at this this relationship between heat and productivity loss, we see for two different emission scenarios. The upper figures show the low emission scenario, and the lower panels show the high emission scenarios, and you see the largest production losses due to heat in the subtropical to tropical regions, and especially for high work intensity. So now with this knowledge and this data, we can calculate now the effects of different adaptation measures. For instance, the penetration of air conditioning, using here also a logistic function based on some also empirical studies, how for different SSPs, like the socioeconomic or shared socioeconomic pathways with a different assumption for economic growth and population growth and education. And here we aggregated according to larger regions like North America, Europe, Africa. And you can see for the different different SSPs, the introduction of air conditioning, especially, for instance, for Africa, low income or developing countries, it will increase steeply in the SSP 5, assuming economic growth in these regions. But for instance, for the more developed countries, the blue and green curves on the top, they saturate at 1, the full availability of air conditioning already pretty in a few years, 2040, for all the SSPs. And then we can calculate we can calibrate the relationship between economic growth and work intensity for outdoor jobs. So air conditioning is of course more for indoor jobs, but for outdoor jobs, we need other types of adaptation, for instance, mechanization, having tractor that are air conditioned. And here we can see again that the economic growth has quite a large effect on the work intensity. For instance, for developed countries, the blue and green line, the work intensity drops quite substantially towards the end of the century, whereas, for instance, in SSP, the top lines, you see that for South Asia, Africa, developing countries, there is not much adaptive capacity, so there is not much effect of the economic growth on the work intensity, so it stays high. Yeah, and using all these assumptions in the GRACE models and looking at the cost of adaptation or the cost of climate change and mitigation for the different types of sectoral adaptation measures, we can see here on the figure that if you look at a low emission scenario, RCP SSP 2.6, then we have this is now aggregated globally, reduction in GDP. We have only a modest reduction in GDP from 0.5% for SSP 1, RCP 2.5, so a low emission scenario, compared to a steep reduction in GDP for a high emission scenario, the red shading. And we also see that for the green shading, the difference between having mechanization or no mechanization doesn't have a big influence on the reduction in GDP, but for the high emission scenario, you see that about 0.4 percentage point of GDP reduction could happen if we take mechanization into account. But we also see that this effect of adaptation is only to a certain extent able to compensate for the heat increase we experience with higher emissions. So by the end of the century, we cannot compensate the heat stress impacts on costs related to worker productivity loss by just purely mechanization or adaptation measures. So its important message is that we need to take into that we need to have mitigation at the same time as adaptation, and to avoid larger costs of climate change. But what we also have to see in this plot is that here we only account for autonomous adaptation. So we don't take into account proactive adaptation. And what we also don't in this plot take into account is other impacts. For instance, here we only look at the worker productivity in the agriculture sector, but we could also, and this is possible in GRACE, look at the same time at yield losses, and then what is in addition to worker productivity loss due to heat stress, we can look at yield, crop yield losses due to heat, and that will add up the cost associated with climate change that we have to compare with the mitigation costs. And so that was just an example. And so we're using a very aggregated and model that underlies, of course, a lot of simplified assumptions. But we can, of course, look at more national scale and cross-sectoral features, which cannot be taken into account in that extent when we look at adaptation approaches on a local level that focus mainly on local climate impacts. So, but both methods can complement each other and should complement each other, because we can refine the assumptions that we take on a national level by incorporating local insights from, for instance, what are barriers to adaptation, what are basically the limits to adaptation, where can we on a subnational level see, for instance, differences in different groups of people, different groups of consumers that can be informed by local studies, top-down and bottom-up studies. So this is one challenge or one opportunity for this adaptation modeling, and the other adaptation opportunity would be to not only look at autonomous adaptation, but also look at proactive adaptation. So include measures that are incentivized by the knowledge of climate change impacts, and then not only looking at consumers and producers' decision based on current prices that are represented in the model, but look at anticipatory adaptation to reduce the future economic costs of climate change. So what we feel is promising is the integration of insights from local and macroeconomic approaches in interdisciplinary studies, and also including the collaboration with stakeholders to inform basically the assumptions that we are taking in the macroeconomic model. Yeah, thank you very much.
Thank you, Jana, for the very interesting presentation. Just a kind request, you know, I'm a macroeconomic modeler as well, so if you can send me the paper, I will love to read it. And we also have many questions and comments, but I'm picking just one that from Piers, that perhaps you are able to read, that basically is asking what can we really reach using this macroeconomic approach, or can we complement this with other methodologies? You partly already answered this because you showed the fruitful integration between bottom-up and top-down modeling. If you would like to very 15-second reply to this, and then you should move to Frank, our last speaker.
Yeah, so the question was how we can really do it, or if we can really do it. I mean,
both, I think.
Both. I mean, there's just a very, simple example. For instance, the SSPs are also very nationally aggregated information, population or equality or education. So if we have more local insights in how disaggregated data for instance, education or farmers' activities, we can include this assumption in the GRACE model, and also governance structures, like governmental structures, allow for these types of adaptation measures that we want to introduce or assume in GRACE to take place. That can change tremendously the numbers we get out of GRACE if we take further information into account to improve our assumptions.
Thank you very much, Jana. Okay, so last but not least, we have Frank McGovern from JPI Climate. I think it will be very interesting to hear his presentation. I mean, of course, all the others have been very interesting, which is adaptation modeling, a JPI climate perspective. So I particularly would be keen to know how this initiative, which is the JPI Climate Initiative, is connected or tackling the adaptation issue. So Frank, the floor is yours. We are going to eat 5 minutes from the coffee break, but I think we are almost almost on time and just a short delay.
Okay, thank you very much, Francesco, and thanks to the organizers for this very interesting event. I'll try and share my screen.
Yes, it is uploading.
And hopefully.
So you can move to the full screen mode. Yes.
Yes.
The one that, okay, perfect.
Okay, thank you very much again. For those who don't know me, my name is Frank McGovern. I am chair of JPI Climate. This presentation is different from the earlier presentations as you will see, I guess. First of all, just in case you're not aware of JPI Climate, what it is, basically it's a pan-European intergovernmental initiative which was established in 2011. It's central to advancing joint research investments in climate change across the European research area. And for JPI Climate and its members, a shared challenge is to understand global climate change, its current and projected impacts on Europe, and to develop knowledge and capacity to enable effective adaptation responses. This challenge has underpinned major research investment by JPI Climate, and I expect it will continue to do so. Just a quick look at our members. There's various types of memberships. You can see most of Europe, most of the European countries are active members of JPI Climate or associated with JPI Climate. How we work, I suppose our vision is to enable transition to a low emission, climate resilient economy and society. And our mission is to provide climate knowledge to inform implementation of the Paris Agreement and SDGs. How we operate, quite simply, we bring together research performers and funders to promote the creation of new knowledge. And that's a very powerful core. In practice, we have a governing board, decision-making governing board, which I currently chair. It's made up of the members from each of the countries. We have a central secretariat who does a very important role in Brussels. And how we advance, we do this via action groups, which are also advised by an expert advisory board. So on JPI Climate and adaptation, we cut across a number of areas. Number one, fundamental science, and I think you will all appreciate that fundamental science is very important. We have funded work in this area from the outset. This includes a joint call with the Belmont Forum. Belmont Forum is a global group that funds research as well. That was looking at climate predictability and interregional linkages. That was completed in 2019. We had an end of term event in July of this year. And out of that, we expect a white paper to identify progress and priorities for the next round of investments, which we will consider at our major meeting in December, which looks at our research strategy and how it has been progressed. We also have ongoing projects with our colleagues in JPI Oceans, looking at oceans and climate. Obviously, the ocean and how it responds and its changes are key to our global future, our shared global future. We're also engaging with Destination Earth in terms of bringing our views and the views of our members to that initiative. We've also been involved with Extreme Earth and support this type of development in going to the next generation of Earth systems models and climate models. And really we see the need for a good and engagement with this process and to ensure that we bring everybody along and bring the knowledge that we've gained along to future initiatives in this area. Key for us is the science policy interface. And the way we're doing or advancing that is to establish knowledge hubs. In this area, we're establishing knowledge hub on sea level rise. Sea level rise is wonderful. Everybody thinks they understand it, but as you all know, it's an incredibly complex area. But this provides us with an integrating platform that can bring together the most advanced or current science and allow us to communicate authoritative knowledge to inform policymakers and decision makers across Europe. It's under development at the moment, but we see this as a key step in bridging that science to policy and practitioner gap. Area 2 is climate services and information. Climate services, I think you're all aware of the various colours of climate services, if I put it like that. JPI Climate, along with our colleagues in DG Research, have invested majorly in climate services. In the ERA 4CS projects, 26 transnational research projects, a budget of 63 million euro jointly between the members of JPI Climate and Horizon 2020. It's coming to a close. I won't go through the details, but you can see on the screen the colours indicate the sectors and the areas that ERA 4CS looked at, from water to infrastructure, to energy, to marine, to agriculture, to decision making, to risk management. And those projects are coming to completion now. We're looking at what's happening next. Where is the next route for climate services? We see them as essential, but we are hopeful to, we'll also be looking at this at our meeting in December, the outcomes from the ERA 4CS project and its views on where we need to go next in this very important area. Next, I would just want to talk about adaptation in practice. And I think the previous presentations have highlighted some of these issues. We have established a series of projects under the heading of Access to promote this cross-boundary, cross-communication research or cross-community research to improve the coherence and integration of and robustness of climate impact research and connect it to the needs, the societal needs, to bring these together in an integrated manner. And also the human dimension is really important here. And I think that's widely recognized or increasingly recognized. We've been looking at this from the outset. Some of the original work we jointly advanced was on the human dimensions. We just had a call, we're just completing a call this year, and we're quite overwhelmed by the response in terms of looking at societal transformation in the face of climate change, and that those projects will be published soon. And finally, I suppose, communicating research or strengthening the international cooperation on climate research. Our project Sincere cuts across a lot of what I've just mentioned earlier, and it also does outreach in bringing in partners from Africa and Latin America, and the essential goal is to realize the benefits of the research investments we made in fundamental science and climate services, and also in the emerging knowledge hubs, so that we get the return from the investment. And we see this as supporting the EU mission on adaptation. And we are looking forward to the ECA, the European Climate Change Adaptation Conference in 2021, which JPI Climate, through Sincere, will be leading on its development. And that provides a key opportunity for outreach and communicating the progress we made in science to policy and practitioners and getting their feedback as well. Communication is a two-way street, as we all know. So, some concluding points. Essentially, JPI Climate is advancing key components of adaptation modelling from fundamental sciences, climate services, up to using climate information. The aim is to further inform adaptation planning and decision-making across the European research area at geographical levels, European, national and local, sectoral responses as well, and to inform citizens. Key to all of this will be to bring citizens along. As we can see in the current situation, public engagement is not easy, but it is essential to make progress. So the development of the knowledge hubs on key challenge issues such as sea level rise will be part of this. And we see major links and synergies with the EU mission on adaptation and the EU adaptation strategy, which was mentioned at the opening session, and also the information platforms that are being developed at various levels, including by the European Environment Agency and by European countries. And as I said, the ECHA conference in 2021, I think, gives us a key opportunity to bring all of this together in hopefully a really wonderful conference in Brussels next June. So that's it, some links there, and I want to thank my colleagues in Secretariat who really put a lot of work into this presentation. And thank you, Francesco.
Thank you, Frank. Just a quick question also for you on my side, because one of the thing that has emerged many times, and it is also at the core of the work that we are doing as a research group within the tender, is exactly how to convey and how to make these all this information accessible. So I was wondering if you can expand a little bit on how in practice, for instance, the knowledge hub on sea level rise is going to work. Just some insights. Because
how it's going to work? Yes, I mean, essentially, well, how the knowledge hubs will work in general is really, it's bringing science to policy and practice. How we see them working will be through, I suppose, first integrating knowledge and science, so we have authoritative knowledge and information about the central topic. Two, having a platform or platforms in which we engage with the stakeholders, whether the stakeholders are in policy or in science. And three, I think we do need major events like the ECHA conference, where we would be able to have that dynamic dialogue. So essentially the knowledge hubs will, in a sense, be like, how should I put it, a streamlined IPCC. I mean, the IPCC is seen as the pinnacle of communication of research to policy, to decision makers. The knowledge hubs won't have the, I suppose, the structures and processes of IPCC, but they will have a really targeted focus. And having that target focuses should mean we can streamline the analysis and integration of knowledge and then communicate it in a more rapid and effective manner to the stakeholders, and particularly our stakeholders in Europe. But these issues, while we have a European focus, also have a global impact as well. So I know that's quite generic, but I hope I've made some sort of attempt to clarify.
Oh, yes. Just to let you know that if you are able to do something which is rapid, we will have a lot of success. Rapid access to the information, rapid availability. I mean, this is one of the key of the buzzword that now is in the policy environment is running. Okay, so thank you very much. Let me thank all the presenters and all the people who are who attended the session for their participation. Now we are having the coffee break. Let me just say that this session will remain open. So and it will start after the coffee break at 11:30 with the second part of this specific topic, which is integrated modeling. So thank you again for everyone, and for the very interesting presentation. Thank you for those who attended, and hope to see you soon. Let me also remind that once again, last time, that the plenary at 12:30 for the and see you soon. Bye.
Okay, it's really good to talk to everyone today, and the first thing I must say is that I do apologize that I don't really come from your adaptation community. I'm flew in from a different direction. So this work very much comes from my collaboration when I was a co-author of the IPCC report on 1.5 degrees. And I didn't emphasize the opportunity to really try and get the adaptation and mitigation communities more connected. So, and we have EU funded project called the Constraint Project. It is really trying to make this connection. Yeah, so I particularly want to talk about the relationship between adaptation and the globally average surface temperature change. So if you look at climate impacts, the climate impacts as coming from the reasons for concern in the fifth assessment report, you can look at the different estimates comparing these to surface temperature, and there are two different axes for surface temperature on this diagram. On the left-hand axis is surface temperature change relative to a present day time frame, and on the right-hand side axis is a surface temperature that goes back to a nominal pre-industrial time. And I want to talk about this relationship between the impacts and the globally average surface temperature change, and the reason why it could be important to consider this is that the physical climate science community where I do work is always revising its estimate of the historical surface temperature, and the estimate in the fifth assessment report of 0.61 degrees change in pre-industrial to this baseline has in fact been revised because we have slightly better instrumentation. We better understand the way the coverage of the Earth in terms of temperatures work, and that temperature could be revised upwards by almost more than 0.1 degrees. I mean, perhaps that 0.1 degrees doesn't sound particularly significant, but if you consider how close we are getting to the 1.5 degree temperatures, it really does become quite significant. So I think we have to think more carefully about the way we translate impacts into a measure of global mean surface temperature, and I think it would be good to begin to document the exact surface temperature the impacts relate to. This diagram is a bit complicated, but I'll try and talk you through it. If you look at a reason for concern, the impact themselves, they haven't actually altered. So the impacts in 2020 are exactly the same as what they always have been, but the fact that we call those 2020 impacts, they do correspond to a different change in the globally average surface temperature. So what was an impact at 1 degree has suddenly become an impact at 1.2 degrees. So perhaps under this idea, we are going to get to 1.5 degrees a bit earlier than we thought we would, but the impacts at that 1.5 degrees will perhaps not be quite as pronounced as they would have been if we estimated 1.5 degrees under what we had for the 5th assessment. So I just think we have to think very carefully about the way we relate impact to surface temperature change. And I also want to talk about the part 2. Want to talk about is the it gets back to Jana's talk from this morning, and also Thomas Wagener's approach of looking at different emission pathways, and I want to talk about there seems to be a bit of a misconception that we really can't make a material difference to the temperature trends over the next 20-year or 30-year time frame. But in fact, some of this work we are doing does indicate about what particular pathway we do take really can begin to make a significant difference to the temperature change over the 20 years. So I think this really does tell us as a community that we really have to think about the connection between the way we implement what particular emission pathway we implement and what are the synergistic relationships in the pathway between mitigation and adaptation. So this diagram indicate the different temperature trends from different emission pathways. We have seen in the near-term past about a temperature rise of just over 0.2 degrees per decade, and if we do not include any future mitigation, we can expect to see perhaps an even bigger temperature change over the next 20 years, or more than 0.2 degrees per decade. But if we are able to get ourselves either implement the current nationally determined contributions or get us onto a 1.5 degree pathway, as in this colors, then we have the potential to try and keep the temperature increases down to about 0.1 degree per decade potentially. So I just want to emphasize that I think it's really good to look at the connection between the global mean surface temperature and the adaptation pathways and the options. And if we do take the correct pathway, we can perhaps do something for both adaptation and mitigation together. So if you want to find out a bit more about the work, this work is done with the open source calculators. And if you want to find out more about the work, I invite you to look at our web pages. Okay.
Okay, thank you. I would say almost perfect timing. I don't see questions from the audience. I just maybe one comment. So here, I think there is a important policy message that, in a sense, what I've been told is that whatever we do, we will see temperature increase, and that, I mean, we can expect to have temperature increase in the next decades anyway, but that there is this, let's say, good news that we can reduce this increase significantly if we act properly and timely now. So
yeah, so I do think that's correct. Yes,
it's an important policy message to bring to the audience, to the policy arena, because this gives the politics have a longer, generally not a longer horizon. This can bring the things within, I mean, with a noticeable effect within a policy relevant, politics relevant horizon. So I think this is good. I see one message from the chat. I see. So Ans asked if RPC 2.6 is not in track for the 2.5 degrees.
yeah, the 2.6 pathway is slightly below 2 degrees, and the RCP 1.9 watt per meter square can pathway. Sorry, I mean the SSP 1.9 pathway is the below 1.5 degrees pathway here.
Okay, so thank you. We can move to the next speaker, I think, Almut. You here?
Hi, I will be giving the presentation.
Okay, so fine.
Yeah, thank you. I am Juliette Maire. I'm a new postdoc in the team in Edinburgh. It's why I'm presenting this work today of the whole team. I'm here to talk to you about a new modeling approach to climate adaptation mitigation in the land system. So, as you all know, with the predicting population growth, I'm just citing few drivers, but dietary transition, we are expecting an agricultural intensification and expansion, and that will have for consequence land use change. And when I talk about land use change, I talk about conversion of natural land into cropland between different crops type, or between cropland to pasture, for example. And these changes are very complex and are depending on drivers, as I say, but also on policy, strategy and objective, and are very responding to very small change as increased food price, for example. And it's well known now that land use change have a high impact on carbon and nitrogen loss, and so give a kind of negative feedback into climate change that will also increase the rate of change of this land use. And as Pierre Forster have said, there is unfortunately at the moment a lack in the land use system modeling, a potential to look at an interaction between climate change mitigation and adaptation. And there it's where the model I'm presenting today, the land system modular model, are set on. So it has been developed by the university, by the team in University of Edinburgh and in the KIT in Germany. It combines environmental, biophysical, and socioeconomic model. It's based on a 2010 country level baselines that have been that get a lot of parameters such as production, consumption, policy parameters, trade barriers, population, GDP, and then takes this baseline to simulate up to 2100 by time steps that could be yearly, to base on the shared social economic pathway with the associated representative concentration pathways that we talked about just before. to give you an idea of the model it's a modular model, and it's included different models that can work and function by themselves or can be coupled together. The first model I want to talk to you about is the LPG gas model, that it's a dynamic process-based vegetation system. And in the Landsea model, calculate all the crops yield and forest yield at the different location, depending on climate and fertilizer use, water availability for irrigation. The more motor of the model is the Plum V2 model that look at the decision made for land use change or for land cover, if you prefer, at all these locations in worldwide. And due to that, you also need to calculate all the economic system on the back, all the demand and trade between countries, and that it's obviously depending on the crop yields that are possible to get on the specific year. It also depends on the climate. And so for that, the Landsea model is also coupled with the Imogen model that take care of the climate and also recalculate the greenhouse gas forcing over time that have an impact, obviously, on the crop yield. Finally, it was a need to look at consumption and dietary that can influence the demand and so the production and so the land use and so the climate. So to give you an idea of how this model are coupled. The aim is to have a modular model that more model can be coupled to it, more module can be used, and also some module can be exchanged with another, for example, climate model if it's more adapted for the use of this model. So I don't want to scare you with this big diagram. It's a simplified diagram of the model, and it's just to tell you that we publish it in the proceeding of this conference. So if you want more detail, look at the different commodities that are used or how it's interacting at the different scales, please refer to the proceeding. But I want to point out a few key features of this model. And the first one is the spatial resolution. It's an interactive multi-scale model that look at as a lot of other model, country level, world trade, but also at a disaggregate grid scale of 0.5 degree grid cell. And that enable a huge flexibility about the land use decision sub-country level. It also integrates, as I told you, a dynamic crop yield, but it also integrates the feeds that are needed and the livestock production from it, but also forest production. And all that are obviously depending on the local climate, the fertilizer use, the water irrigation, and also, for example, CO2 fertilization. But all these crops and the production of each time step are set into a world economy balance, and that's a uniqueness of the model too. It doesn't try to, every time step, to have an equilibrium in the economic world balance and allow short-term deficits and surplus that are a lot more realistic of the current system. It also includes trade, so trade barrier, but also subsidies to some commodity at the country level that are more optimal for this kind of calculation. So when the model runs, it can estimate environmental impact and socio-economic development impact. And when I talk about this, I talk about ecosystem services, nitrogen and carbon losses, water use, but also new implementations that will be able to look at wildfire impact on the system. And in terms of socio-economic development, it was very interesting and very important for us to look at human nutrition and hunger factor, for example, of how the change will be made in the system and in the prediction will impact that. So the concept of the model is to make it run under different scenarios, and these scenarios are often used to look at shock. So as we talk about different shock, I want to talk to you about different applications of this model. So I couldn't talk to you about all the applications that I already have published, but I just wanted to put some key words that are looking at, for example, biofuel and energy. So for example, is it possible to maintain the climate under 2 degree increase of temperature, but still have a high demand of biofuel and bioenergy? Looking at dietary transition and shocking the system, it's very important to look at food resilience, for example, but also at the impact of extreme weather event and this impact can be on different scale. So that enables us to look at the resilience, and I couldn't do this presentation without to talk about COVID-19. So we are in a project at the moment to look at the impact of such a shock like the pandemics that are shocking the food system at the moment, how that teach us more about the resilience and where the resilience are host in the system and what can be improved. And that enables us to look at different interaction between the mitigation, so the policy objective, and the actual decision of the landowner or the institution that can sometimes be synergic, but can also be counter-interact in terms of the aims to regulate the climate or reduce its effect. So this model, I hope I give you a good overview of it. It's a platform to better understand the interaction between climate adaptation and mitigation. And it's to identify and teach and look at the impact of policy and action to try to see which one are the most suitable in the long term. So thank you very much, and I'm happy to take any question. And for that, I would like to invite my two colleagues, Peter Alexander and Almut Arneth, to help me to answer the question. Thank you.
Thank you. Again, very perfect timing. I do have a question from the audience, from Francesco. He asked whether the fact that we can go for such high spatial resolution enables us to really increase the realism or not. So will you be confident to suggest a policy for a given grid cell based on the results of your model? Or can you suggest how to correct the user interpretation of results?
I don't know if Peter would like to answer this question, or should I take it?
Yeah, so I mean, obviously it would be foolish to try and give policy recommendations at a grid cell level. However, that doesn't mean that looking and trying to model data at a finer spatial resolution isn't necessary really to understand the sort of the more aggregate responses. Clearly, particularly when thinking about adaptation, that's going to vary very spatially. So in either changing crop types or changing management practices of the same crops, increasing irrigation, for example, and those type of responses are not well captured by CGE or other type of models, which tend to operate at a much more aggregate spatial scale. But here we're using LPGS, which maybe Albert will want to talk about a bit more, to sort of try and represent the vegetation response at that sort of much finer resolution, and then the sort of the human decision making at that much finer resolution to try and capture some of those behaviors. And in one of the papers we've already published, we can see how that sort of autonomous adaptation reduces the land response, the land use decision making response, compared to some of the previous work done from the IAMs. So although to recap, although I think you're quite right that to sort of suggest that in this grid cell we would expect this response and therefore this policy in that very specific way is not likely to be achievable. I think still we need to represent that spatial dynamics far more than has been done in the past.
Thank you. That's really perfect timing to the second. So let me just give the floor to the next speaker, Roger Street.
Thank you very much. I'm hoping you're now seeing my screen, and hopefully that'll be useful. What I'm going to talk about here is really looking at climate services that are supporting adaptation modeling. This is a very key issue in terms of what we're trying to achieve. That's not where I wanted to go. Let me just start again. Apologies. Anyways, so what I'd like to do is start to really look at this from what do we know and where do we understand the gaps are and where are the emerging issues that are coming out in terms of the climate services that are needed to support adaptation decision-making and adaptation, and then providing a forum for or a mechanism by which the results from adaptation modeling can reach the users, etc. And I'm going to take a look at, start with in 2015, the European Roadmap for Climate Services, but also then look at 3 reviews that have taken place. The first one in 2017, then in 2019, and then the most recent one in 2020, and then come up with some conclusions regarding where to go, where we need to go next. Now, the European Research and Innovation Roadmap for Climate Services, you've already heard it mentioned today, was really a framework to engender that discussion. It was what needed to be done, who are the relevant actors and stakeholders, and looking at solutions and pathways to enable the development and use of climate services. And it came up with 3 challenges, and I'm not going to go in detail on these, but one was to enable that market growth. How could we enable that market growth going? And that's the nature, assessing the nature and growing and demonstrating the added value of a climate service market. And when I'm talking market, I'm talking about both private and public sector markets. So we also needed to look at building that market framework, you know, the infrastructure, the communities, the standards, the quality assurance, and all of the legal aspects and international cooperation that are essential to building climate services and enabling that market growth. But also, and then the third challenge was enhancing the quality and relevance of those climate services. You know, the support of information and the, you know, enhancing the quality of the information and understanding user needs. So this came out in 2015, and in 2017 there was an attempt to say, okay, how far are we moving along in this? How are we making progress? What more was needed to be done? And a position paper was prepared by Climate Europe, and it was a position paper based on a workshop that engaged users, providers, and researchers. And there was about 100 of us in the room that looked at these and looked at where we needed to go. And one of the things that came up for this, I thought was very useful, but it was consistent with the roadmap. It validated the roadmap, but also focused particular areas. And one of the particular areas that came up during that workshop was the need to continue efforts focusing on building the market framework of that infrastructure. You know, there was a real push and a desire to move in that area, but also there was concern that came out is that in order to do that, they had to retain an appropriate balance of investments between the research that was needed, the climate change research, the climate science research, the climate, you know, understanding the social and engineering aspects that were needed, but at the same time supporting the innovations. So there needed to be this balance that was, and there was a really stress on that. The second meeting, the second assessment that was done was came out in 2019. And again, this was a number of European experts that got together under the auspices of Climate Europe to look at the challenges and where we were, both in terms of climate modeling and climate services. I'm only going to focus on the climate services aspect again. And again, you can see that there is this consistency with the challenges and activities within the roadmap. But one of the big changes that occurred, I noted occurred during this one, was the emerging focus on better supporting solutions, adaptation and resilience. There was getting away from just understanding the impacts to also looking at what services and what information was needed to support solutions. So there was recommendations. The recommendations are, you know, supporting the formulation of adaptation strategies, understanding requirements, decision-making contexts, and foresight for climate services. So reflecting those in the climate services that were being designed and developed. And enhancing diffusion of innovation, getting that diffusion out there. There was a lot of innovation that comes through these research projects, but just weren't getting out to the users and getting out to those purveyors and other people that were getting climate services to the users. Assessing the value is still an important aspect that needed to be done. Standardization is still needed and is a big necessity. But then in looking at this framework of the climate services, strengthening the link between the climate modeling and climate services community. They each have requirements, but unless they work well together, we're never going to realize the benefits that are needed. And I apologize for this slide, it's a little smaller font. But then the most recent one was the Arneth for climate services. And this is the activity that Frank mentioned this morning, before the coffee break, I should say. And it came up with a number of highlighted challenges. And what I've done is I've arranged those in the context of the 3 challenges from the roadmap. The majority of potential users are not convinced of the value of climate services. They don't see the value of them. And so there's still a fair amount of work to do there. And there's a lack of an overarching framework and metrics for evaluating climate services. So this is really something where we need to enable that market growth. Building the market framework, there's need for a platform to facilitate sharing experiences and lessons learned. A significant contribution and research is being done within the private sector, and there's a reliance on the private sector for this, and we're not getting that platform where there's an exchange and sharing that's going on. Coordination at the European level in scenario development is a necessity, and we need to explore and identify good practice business models. Enhancing the quality, not necessarily do users see climate change as a standalone risk, and it's understanding that. And when we're doing our modeling and we're providing information, it's understanding that and supporting, and then it's moving away from just this incremental changes to more supporting transformational adaptation and transition. We're hearing more of that coming from the users, and they want to have a better way of looking at that. And many research projects, I'm not going to go through all of these, many research projects actually stop before reaching the stage of providing a standalone operational service. It is not being supported through the funding that they're receiving, and so it stops there. So that there's really a necessity to move beyond that. How do we move forward on this? There is an increasing demand, broadening and deepening for climate services, but it's still in need of encouragement, increasing the marketability and quality. That's enhancing the push, I should say, and enhancing the service pull. So we need to do both in terms of doing that. And we're talking about climate, you look at why is this increasing demand? Climate resilience and low carbon focus. The Green Deal and COVID-19 recovery, investments in Europe and elsewhere. They're all talking about climate resilience. They're all talking about low carbon or zero growth. We have to be able to get at that information. And I think it's essential and be an information that can support those. Increasing demands. Requirements in investment in the banking sector alone are having significant implications for climate service, and the demands coming from those sectors are phenomenal right now and ever increasing. The EU and Horizon Europe mission. I've heard it even say that the European Horizon missions are missions impossible without climate services. So that's fundamental importance of that. But also this increasing focus on solutions that's coming out in the EU adaptation strategy, coming out in the EU Horizon Europe missions. It's all about solutions, getting action on the ground, and therefore we need products and services and advice and resources that can inform and support the solutions and solutions management. I believe very strongly that there's a need for a systematic assessment of the remaining and emerging challenges that explores a number of different areas. And when I'm talking about systematic assessment, this has to be assessment not done by researchers alone, not done by just a gathering of people. It has to be involving both the private and public sector and the private climate service industry as well. And we really need to understand the extent to which the requirement for solutions and action supportive climate services are reflected in the demand side, but also supported by climate products and services currently available and under development. So what is currently going on? There's not a clear and comprehensive picture that we can get at. The extent to which current research and innovation efforts and directions related funding are considering the need to support the evolution of climate services. This evolution that's going on is quite significant. It's not a revolution, it's an evolution, and we need to be able to see how that's being supported, the foresight capability that exists within that community, and the extent to which innovations are directed at enhancing the relevance, usability, legitimacy, and credibility of solution-based climate services products, consistent with what are and will be required to inform those actions. So it's really looking at that. There's sort of an overarching question here. Are processes and support mechanisms that are intended to facilitate the transition of research projects and project-created activities, are they sufficient and effective? And what more, if anything, is needed? And I think these are overarching questions that need to be addressed through this systematic assessment. Thank you very much.
Thank you for the very comprehensive presentation. I have two questions. Perhaps we can, one is quite short, so we can probably address both. The first is, are people really understanding climate services as climate services? Many institutions may utilize climate services, but without naming the service as such. So are climate services a thing identified in the policy institutional area?
It's actually a very good question, and it's one I've spent a lot of time. I work in a number of countries around the world with climate services and developing that capability. And one of the most difficult terms we have, especially difficult things we have when we're talking to those people that should be using this type of information, is the word climate services. It is a very cumbersome and misunderstood term. I was on a meeting yesterday where they were talking about, instead of climate services, they were talking about adaptation and solution ecosystems that includes climate services, and that's in the banking community. So there's a number of different things that are out there that are being used. I think I'm not a big pusher that we have to come up with a single accepted term and what that means. I think what it has to be done is that there has to be a clear understanding when talking to people that what you're talking about is knowledge, data, and resources that can support decision-making towards and support decision-making and climate action. That's what it's all about. That's what it's trying to do. It's trying to support decision-making and decisions related to climate action. And that's both mitigation and adaptation.
We have 1 minute to spend a little bit on climate services and our role in the Green Deal. That was a request from Hans. Do you have any further thought about that?
Yeah, I think this is one of the things that I'm really interested in. And the Green Deal, I think, is very much provides an opportunity for us to redirect and focus climate services much more effectively on delivering the adaptation, resilience, and mitigation that is required to deliver that Green Deal. And this, I think, is something that we need to spend a lot of thinking on. And that's why my reason for the assessment, because the Green Deal and the missions and a number of other things are all focusing on solutions. And I believe that there's still a fair amount of work that needs to be done to move away from just focusing on risk and impacts to actually focusing on that required to deliver those solutions.
Thank you. That's perfect. We can move to the last speaker, Bart.
Yes, thank you. Bart van der Hurk. Can you make me presenter? So I'm Bart van der Hurk. I work at Deltares in the Netherlands, which is an applied research institute devoted to water. And of course, there's a lot of climate related to water. What I would like to talk about is indeed the search for impact-relevant climate information, and that is not as trivial as Roger Street also has pointed out. And what we normally do, making climate assessments and climate impact assessments, we tend to normally follow a sort of a consecutive chain of cause and effect pathways, and where we start with some exploration of global economic developments leading to global emissions, which leads to a climate response in terms of global mean and regional patterns of temperature and related variables. We appreciate that this global picture needs proper spatial temporal downscaling, and use climate models for that, regional climate models for downscaling. And we also use regional specific and impact-oriented impact assessment models like agriculture, forestry, whatever, which is fair. But you know, there is a caveat in this approach, as we all realize, is that with every step that we take in this chain, in this cascade, uncertainty increases. The envelope and the degrees of freedom of the system increases as the stepping is proceeding. And this method, this approach, this framing, it is successful because we really can, you know, put on the back of an envelope the conceptual picture of what climate change impacts look like if you have these IPCC endorsed socioeconomic scenarios as a reference. But it is mainly designed to display drivers, and it's not really focusing on impacts because there the uncertainty is large. And so we really need to use additional bottom-up procedures, and that is not new, but I think literature is maturing on concepts that start with narratives and storylines with a much more, say, impact-oriented origin. And also the new AR6 IPCC report has in its glossary definitions on storylines that are used to make sense of this complex world, but to stick with some causality, with some that we are using explaining variables that are put into a logical or causal sequence and reasoning. But it is essentially that these storylines are conditional pictures of futures, conditioned on assumptions or scenarios or whatever. And as such, they are not intended to give a probabilistic assessment of the impact as such. It's really oriented to, as I said, to make sense of this whole complexity and actually to enrich the picture of potential impacts. And I'm just going to illustrate a couple of older and newer examples. There's many of these, but just as an illustration to help the discussion that is maturing this approach also in scientific sense. And what I'm going to discuss here is the approach of in the Netherlands, where we produced climate change scenario storylines based on a very large number of IPCC endorsed projections. And also will detail a bit more results from a currently running European research project called RECEED, and that is looking at physical climate event storylines, where we look at climatic features like individual weather events. But let's start with this climate change scenario and these climate change storylines. What this project was about, and I've presented it before, so people may know about this. But what the essential element of this program is that we did produce climate change scenarios for the Netherlands, for to say, that are rooted in CMIP5 global climate projections with a lot of regional downscaling. But the essential step of the scenario production was actually that we are aggregating this very large plume of potential futures into only 4 discrete scenarios with a selection of assumptions leading to these 4 narratives, if you like. And we disaggregated or aggregated, I must say, this large ensemble into actually just 2 directions of uncertainty. And of course, global mean temperature change is a big driver of future climate expression in the Netherlands and surroundings. So that is logically to have that as an axis. But we took temperature rather than an emission pathway. So it's really the temperature that drives the climate system. And on the vertical axis, we also discriminate, regional feedbacks if it comes down to hydrological responses. Precipitation changes vary a lot with changing atmospheric circulation conditions. Models don't agree on that, so we had to, discriminate, say, large and smaller changes in local regional circulation. And a similar story could be told about sea level rise, where, say, cryospheric responses, big ice cap responses, also have a large uncertainty and give rise to either lower or higher sea level rise values. But so we sort of took the courage to condense this order 250 projection into just 4 locally relevant scenarios. And in addition, of course, we provided meteorological quantities that are well known to practitioners in the field. There's lots of water managers at a very local level, at the national level. There's a lot of urban planners, agricultural planners, whatever, that are used to work with weather data to build their historic analyses and to make some forecasting things, etc. And we stick very close to that experience with meteorology. And so we expressed our climate variables into quantities that can directly be inserted in the applications used to make these impact assessments. And we have very positive feedbacks on both that courage to make this selection of storylines and not to force these practitioners to run 245 scenarios, and also to map it towards entities that are very close to their current practice. And so it's well embedded in the Dutch management system, and it's even in law that local authorities have to comply with these and these scenarios before 2050, etc. That's example 1. The other one is more on an event based. RECEED is a project that was responding to the call from the European Union that was supposed to map European impacts of climate change features happening anywhere on the planet. And there's lots of, socioeconomic connectivity between Europe and food producing areas and trade areas and financial interest in many areas. And when designing this project, we immediately got stuck in that formal risk assessment where we would combine some kind of probabilistic assessment of drivers with very complex multi-factorial impacts. And we just couldn't think of a good picture to get it into a formalized quantitative risk estimate. So instead of that, we are now focusing on deriving a couple of very well chosen, targeted, illustrative event storylines rather than formal risk assessment. And I'm just running you through a very simplistic example, but it brings across the point that needs to be made, and that is, of course, that we need to detail the structure of these storylines a lot with local practitioners and experienced people, and also have to think very carefully about their framing and the purpose of these. And one of the sectors that is receiving attention in our project is, of course, the financial sector, and there's many financial sectors. There's insurance, there's private equity, there's all kinds of things. There's also public finance sector, and for instance, the European Union has a solidarity fund that is exposing or that is disbursing sums of money to help assist repair or mitigate climatic or environmental disasters. And on the upper left picture, you see the time evolution of both, say, the disbursement, the cash flow from what is it, 2002 onwards, in response to disasters that happened in the European area. But one of the European subdomains is the Caribbean outer reach areas, and that is pretty sensitive to hurricanes, of course. And you can see that is labeled orange in this picture. That is a very minor part in the overall. The other floodings and earthquakes on the European mainland are much larger in that sense. But we see that for 2016, we had this big Italy earthquake that really used all of the money that was in stock for that European Solidarity Fund. And a year later, we had Irma hitting the Caribbean, and that is led to actually a negative position of the cash flow, and that in itself is a risk. This fund cannot afford to get into negative positions, because then it has to collect new money or lend it on the market, etc. And there is an interest to map the risk of these cash flow deficits, and that's what we did by for the present climate, not even looking at climate change, but just mapping, you know, potential alternative pathways of this hurricane that we had, and there is good technology around in insurance companies that use empirical models to generate many alternative cyclone pathways, and we combine that with some damage estimation, and then we could make a much more, you know, a range of potential cash flow exceedances in response to that hurricane feature. And then if you look at the yellow line in the lower figure, that is mimicking the cash flow on the upper right level, but you see that this the hurricane in 2017 and 18, by the way, is yielding quite a bit bigger spread in that cash flow number. Because if we can think of alternative hurricane tracks that re-enter countries or hit more fully on a country, and we see the risk of a multi-year low cash flow volume in that European Solidarity Fund, and that is expressed as a potential risk. This can be done analogically in analog to, say, future climate settings. We can and are working on procedures to perturb climatic factors like sea surface temperatures or circulation statistics around related to the circulation, that all affect pathways and probabilistic intensity classes of hurricanes in future climate settings. And so we are able to reproduce this historic evolution of the cash flow trouble for a world that is 2 degrees warmer, to give another, you know, richness in the future risks, assuming current conditions remaining the same. But it at least allows you to combine multiple drivers for this cash flow risk, not only climate, but to relate these climate drivers to other drivers. So this is just as an illustration for this storyline approach. So there is a good reason to dive into this a lot. It has to be very context specific. That is clear. In this example, there's so much information from local practitioners, and we have to combine so many impact drivers. Some of them are even interacting. It cannot be treated as a probabilistic statement on the likelihood of this cash flow problem, but it gives you a much better idea of where actually the maybe hidden or explicit risks are lying. So it is really intended to provide additional risks of a richness in pictures for implications and maybe also adaptation options. Of course, we do have to follow physical reasoning, and we have to make sure that our storylines, they represent plausible situation, and if possible are rooted in probabilistic statements on, say, background assumptions. And so we do definitely have to link them to these temperature projections and the physically supported response of hurricanes there, to be able to be useful. I mean, it is not science fiction. We really have to have physical grounds there. But the probabilistic element can be rooted when looking at, say, the major drivers of these alternative pathways, like climate change. And finally, re-emphasizing the need to bring in a lot of local information in this practice. But we are running 1 year now on this project, and we've worked on quite a few of these examples already. And for me, as a climate modeler by training, I've been really surprised and intrigued by the complexity, but also pleasantly surprised to see to see the role of climate in this whole complex decision-making topic that is taking place in this adaptation level at the practitioner's level. So I think that is what I would like to discuss on storylines. Happy to answer questions.
Thank you. We still have a couple of minutes actually, because I mean we managed to save some time during the the session. We have a question from the audience, which Thorsten asks, if you consider stakeholder relevant impact thresholds, as for example in the scenario discovery, to decide what storyline corridors lead to significantly different decisions, or is the storyline definition independent of decision relevant outcome?
No, thank you for the question, Thorsten. No, it's definitely not independent. But I think the decision-sensitive thresholds, they basically depict the kind of information that you want to extract from say the physical part of the storylines. I mean, these storylines, they need to have and a story is kicked off by, say, a climatic event like in this project, but it is of course followed up by a socio-economic teleconnection, and that is as essential of the storyline as the physical part of it. But we do appreciate that there is quite a lot of non-linear propagation of say climatic features on in that chain, socio-economic chain, that is very sensitive to thresholds, and so indeed these tipping point or threshold elements that are taking say, or are of major importance in the final decision making, they have to be mapped back to these physical elements. And it can well be that within, say, the relevant realm of acting or of adaptation, climate is not a major driver at all. There's other drivers that are much more dominant. The threshold is not being challenged by the climate projections that we use. But we can also alternatively find examples where a very minor change in the climatic feature can actually be emphasized or accelerate, increased by very sensitive socioeconomic sensitivities. That is, and probably there is a very rich relationship between that threshold and the climate impacts. But that is, of course, where we have to focus on, that we extract the relevant information from the climate projections that map on those thresholds.
Thank you. I really need to close the session and to thank all the speakers and participants for this very exciting and interesting session, and invite everybody to join us at the wrap-up plenary session starting now. Yeah, you should have received the link, but I'm typing it on the chat now. So have a look at the chat, and this should bring you to the plenary. Okay, so see you there. Thank you. Bye-bye.